Yeah, I have this APC Smart-UPS 750. Yeah, I won't zoom in. Laying around for a while. Yeah, it's defect. It does basically nothing, and yeah, it's from a customer. The batteries are out, hopefully, because I don't want no leaking lead acid batteries around here. And yeah, we'll take it apart and we try to get a glimpse how it takes inside. So the easiest part is obviously that's normal maintenance. The front plate, which comes off, should come off quite easy. Nothing much to see there. Oh, here. Snap in the whole front plate assembly. Oh, that's easy. And, oh, look at that. Yes, even, okay, I'd zoom in later when I got more cable, or I can move it, and we can try to zoom in. Yeah. That seems to be a specialized chip just for the front panel. Or maybe I rewatch it later and I'll tell you what kind of chip that here is. But obviously it's a bus connection. I mean, we have 1, 2, 3, 4, 5, 6, 7, 8. Yeah, must be some serial bus connection with just 8 connections. Oh yeah, here. That's a good shot. I can read the chip number from here later. Okay. Let me move back and let the camera please focus again. Oh, I have to zoom out. Makes things easier. Okay, so we have, are we in focus? Yeah. We have the battery compartment, which is now obviously empty. As I said, I didn't take the leaking lead acid battery and some, yeah, this is not aluminium, this is real metal. And these things are heavy. Details on the front plate, yeah, a little bit of plastic to get the light from the LEDs on the front panel, not on the front panel, you know what I mean, to the front, yeah, nothing special. Some rubber buttons that, yeah, this must be conductive rubber at the end because there are no micro switches here, just some contacts which are pressed by the rubber, but yeah, it wasn't the buttons that failed, but the whole thing went bad basically. So where to go from here? We need screws, obviously. No significant screws on the back. Yeah, seems to be they are all down here, and I need the right screwdriver for that. 1 second. Yeah, I want to point out these are not good screwdrivers. Just in case you watch that channel with the you know, cursing Canadian guy. These are not good. There are German screwdrivers, I mean, sold in Germany, probably not made in Germany, but they are not good screwdrivers. They're okay, but they are, yeah, okay. Forget about the screwdrivers. Okay, the screws have these funny washers on them, which basically do nothing in real life. But anyway, mechanical engineers in the electronics case or enclosure business still like to use them. I have them also on my vintage power supply I'm tearing down. Okay, and does it slide? Or is there any other way to get that off? It doesn't really slide, but it bends. Can you see that? Yeah, you can see that. It bends, comes out. Okay, so some ventilation at the side. Obviously only passive ventilation. No fans. But I never heard a fan in that kind of UPS. Nice big plastic isolation shield on the back of the main board. Oh, that comes off easily. It's always good to have some isolation material handy. And this is nice and big. And I guess rated for mains power. And then we have the main board again with 1, 2, 3, 4, 5 screws attached. And these are also some quite sturdy screws to attach a main board, but okay. So the main board sits upside down in the case. And yeah, there's another screw. It didn't want to come out. Oh wait, more screws here on the side. Maybe that will help. Oh, okay. Now it's starting to come apart. Okay. Now it's basically, sorry, can you see that? It's basically these two cables, which are, wow, let me zoom in on that. Quick connects with our spade connectors with this releasable snap-in mechanism. Not too bad. Still a pain in the ass. Two transformer connections. Okay, here goes nothing. I can always review the video. Come. Two black connectors. A very well isolated spade connector. More connections to the transformer. Okay. That's actually quite simple. Now we have only left one more battery connection and a connection to the empty expansion port that was here. And yeah, black. Okay. Yeah, I have to cut that cable. Okay, pliers are in. And that is the board in all its beauty with the little satellite for the front panel. So, a whole lot of big relays, but yeah, maybe I sit down for that and we have a look and go over the board. And I try to remember which connection was what. For that I probably need to review the clip up to now. So hopefully I was able to clean up all that connection mess on the main board. Just for orientation, we have here a big capacitor and 4 heat sinks. And yeah, that's supposed to be the capacitor and the 4 heat sinks. And the simple part is that soldered black connection here went to battery disconnect on the back side. Oh, it's still heavy because the transformer is in. Oh. Let's see. Not a switch, a connector. Battery disconnect. Just in case, I guess. Put that out of the way again. And yeah, then it goes to the minus of the battery. The other connection, big connection here, red. Here, red, right beside the black soldered one, goes to battery plus. And interestingly, inside the battery compartment itself, yeah, loosey-goosey. I mean, these APC batteries are basically 2 batteries side by side, and between the batteries is a, yeah, 60 amp fuse, just in case. Okay, that was easy. Then these connectors here, neutral out. They are basically the same. Okay, there's 2 times neutral out, and there's 2 times hot out. And you can see, yeah, they are connected. It's the same copper on the board. And these go to, yeah, white and black, somewhere, yeah, west of our heat sinks. White and black go to 2 times 4 IAC output connectors. And I lied. It's only 3. Okay. 2 times 3. Whatever. Nobody can read that afterwards. 3. And power comes in, obviously, through an IC power in connector, and there is a resettable fuse at the side. This is this connection, and mains ground is distributed also to the case, but distributed directly to the output ICs. And this is not a resettable fuse, but drawn as a resettable fuse, but it is resettable. And this goes to white neutral and black hot in, which is right here on the board. Okay. And then we have the mysterious black and white thingy, which goes to at least 1 transformer coil. And the fact that these 2 are near the heatsink, yeah, I mean symmetrically at the heatsink, that leads me to believe that this is actually for generating 230 volts mains from the battery, or let's say this is the low side of the big transformer. So unlike an inverter where you work with high frequency, obviously they don't work with high frequencies switching to generate 230 volts output. No, they drive a big fat old transformer. These are the inputs. Can you see the thick copper there? Yeah, I get a meter out in a moment, and we can see how this all works. On the other side of the transformer, which is yeah, much thinner copper, so mains voltage, has a 4-pin connector, which goes here on the board, right to where neutral and yeah, neutral and hot comes in. Yeah, yes, hot in and neutral in. Yeah, some thingy to suppress spikes, I guess. Or restore. No. Metal oxide resistor. Yeah, now I have it. Yeah, let's probe a little bit on the board. I mean, this is now powered down, but still, if you connect external devices to an APC in that state, they should be supplied straight with mains in. So let's probe how the connections are switched by all these relays when there's really nothing happening. Between neutral in and the transformer connections. Okay, this is some meg ohms. That can't be it. This is 0 ohms. Okay. I mean, complete isolation. 5 meg ohms, 0 ohms. So there's not 0 ohms, you know what I mean. Some meg ohms again. And nothing. That's interesting. Okay, let's probe hot in. Okay, a few mega ohms. Nothing. For something mega ohms. Nothing. That's interesting. So then we take neutral and neutral out, and that's also a few mega ohms. Oops. And yeah, basically isolated for mains voltage purposes. I'm a little bit flabbergasted. Maybe I have no. Hot in, hot out. Nothing. 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 I thought this would be easier. Yeah, and the transformer connections, I mean, okay, this is double-sided. I hope it's only double-sided. This goes, they go all under this big relay, and that's actually a capacitor. That one, big capacitor. This looks like a, yeah, common mode choke, another big capacitor, and 2 metal oxide resistors here. So this is, and this is all input filtering, or yeah, output protection, however you want to view it. Another big capacitor, oh, not big, but 1 microfarad. Okay, 250 volts. That's the same. That's also 1 microfarad, 250 volts. Yeah, and this is also just a capacitor. Probably can't read it, but it's yeah, 2.2 microfarads. And then we have relays. These are relays. These are all relays. Yeah, etc. This is actually 12 amps, 250 volts. Yeah. Can't really see it. But obviously, if your APC is not connected to mains power and switched on, the devices connected to it are also dead. I didn't know that. I wouldn't have expected that. I mean, yeah, I would have to map out that stuff. That's a little bit more work. But maybe we can approach the thing from a different angle and have a look at the heart of the operation. Sorry for that. The transformer. So This has nothing to do with the transformer. This goes to the battery compartment. But we have here the two connections to the transformer, which I said this was white and black cable going somewhere to a transformer coil. And that coil has a resistance of come on. Basically nothing. Yeah, I would need a milliohm meter. Yeah, basically nothing. Oh, say 0.2 ohms. Yeah, we're not talking about inductivity here. Just 0.2 ohms. And just to check it, and that's the low volt side. Just to check if there's any connection to the high volt side. Nope. 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 Yeah, don't have to switch that. Nope. Okay. So at least we know that the low voltage side, which is driven by the battery in case of a total power failure, is isolated from the mains side. Now, from white to black, we have not much either, but a little bit more. I'm jotting this down at the same time. So from white to yellow, we have 5.0. And from white to blue, we have 5.3. And between black and yellow, we should have, okay, it says 0.5, 0.4, yeah, that matches. And between yellow and blue, we have again 0.4. And now we could also measure between yellow and blue. Obviously 0.8, the sum. Do I have all combinations? Yeah, I guess so. So that tells us basically how this transformer works. It's basically kind of a non-isolating variac. So this thing looks like this. You have a big coil, and yeah, obviously you have the core, and the core is also, yeah, that's the same core, okay. And this one goes basically here at one end. This one goes to the other end. And then we have two more, which are not equally distant, so have not the same number, the equal number of windings, but have a lot more windings. And if we just go by ohms, this is 10 times the windings, 11 and a half times the windings. So this should be 1 to 1 to 11.5. Devious. Did I mention that this is basically not a continuous variac, but it's a variac where they can switch. I mean, in the specification of these things, they say they can basically compensate high power and brownouts. And how they must do it is they put, and I'm not sure, I have to trace out the relays, but either way they connect mains here or mains here between this input on the long coil and this input, and then they get the output voltage between this connection to the coil, the winding, and either when the mains voltage is good, also basically shorting out the transformer, giving mains directly to the output, also to this coil, or if mains goes too low, below a certain point, they switch over using the relays to these extra windings, and this gives you an extra amount of AC voltage, basically neutralizing the brownout. And if mains voltage goes too high, they switch over the output to this connection to the winding, which is 1 over 11.5 less voltage. Sorry, do I make sense? It's rather primitive. It's really primitive, and they don't switch it electronically, but just through 1, 2, 3, 4 relays. And I mapped these relays out, and we'll see. The only thing that I don't understand is why I don't have any direct connections. Maybe there's a permanently fusible element somewhere here on the board. I have no idea. The other way around would, of course, be connect the output permanently to these 2 points, and then have mains connected here and switch mains between the 3. You have basically the same result. It doesn't make a real difference. Okay, looks like I have to map out these relays a little bit in detail. Okay, I'll come back to you when I've done that. I ended up desoldering the relays from the board so I could map it out, and things become a little bit more clearer after that. Put this away. Sorry. Yeah, it's the next day and my throat is a little bit raw. It's a weekend. Yeah, anyway. Where were we? Yeah, exactly. How the relays are switching the autotransformer. And yeah, this looks a little bit convoluted, but from the backside, seen from the backside of the board. But it's actually quite simple and primitive. So the first relay, that one, is actually quite cheap and simple thing. Song something something, and it's quite slow, 20 milliseconds to operate, 50 milliseconds to release. But we can completely forget about that one, because that is basically switching both lines of the mains input, neutral in and hot in, on and off. That was the reason I couldn't find any direct connection for neutral between the input and the output. Yeah, so really quite simple. The one of the better relays, if I can see it, Zettler. Yeah, these are brand relays, Zettler AZ697 series. They only take 8 milliseconds to operate and 5 milliseconds to release. So you can basically switch them yeah, in the time of one AC wave. Yeah. And the first of these is basically just switching the hot out on and off. Yeah, they done it a little bit funny. Yeah, I don't know why they did it, but that's how they did it. And the other two, they really do the work of stepping up, stepping down the output power, so the hot out. So for example, our relays are now normal off. So if that is on and that is on, hot in goes through the right connection of our transformer. And I found out it's an Autotransformer. We call it an Autotransformer. And our hot out is going to the same connection of the Autotransformer. So basically we have no step up, no step down, it's one-to-one. And yeah, before tracing everything here manually, I made a little table. So basically if one is off and relay 2 is off, neutral is always connected by the autotransformer to the left side here with the many windings. Both in and out are connected yeah, to the same output of the autotransformer, so you have one-to-one. If you switch one relay 1 on, yeah, that was that up here, and yeah, you see it comes here, goes, if it's on, to that pin. In comes up here to the very right, and out is one winding down to the left. So we have a 1x step down. And so on. If 1 is off and 2 is on, they switch over in to the left. Yeah, that's actually quite indeed. Here is hot in, and if this is on, this goes to the, not to the neutral, but to the left of the low count windings of the autotransformer. Yeah, out stays on the right, so we have in the autotransformer yeah, I call it a 2x step up in voltage. So you would use that setting, for example, if you experience a brownout on your mains, and then you can step up the output voltage without involving the battery and stuff of the UPS at all. Same here, if you have a slight over voltage on your mains, you can step it down one step and without involving the electronics. Of course, a brain box, which is quite massive. We will later on have a look at that side of the board. Does all the thinking when to switch these relays. Oh, they're gone. They're here now. Yeah, and the fourth combination is of course both relays on, and then in is still on the left, and right out is to the middle, so we have a 1x step up. Why they don't have 2 times step down implemented, which would have been possible, yeah. We have enough windings, and I don't know, but they didn't. I found one hint in the manual, and it says if you have on the 230 volt models for Europe, if you put the input 230 volts, you can, within the options of the device, say you want a fixed output voltage of 220 volts. And you have, I guess that's one step down. And if you have, again, 230 volts, you can also step up, fixed the output voltage to 240 volts. I guess that's to accommodate different equipment. Older equipment, for example, here in Germany was specified for 220 volts. Nowadays we have 230 volts. But there are also regions on this earth where your standard mains voltage is not 230 volts, but 240 volts. So you can run that also on its nominal voltage. However, if you use the step down option or the step up option in the settings of the device to permanently step up or step down the voltage, of course you have less reserve if you have a brownout or the voltage in your mains is spiking. Yeah, quite primitive, but effective. Yeah, okay. Let's continue with that stuff here and have a closer look. First, yeah, let's see what kind of filtering they are doing, because I'm a little bit concerned about the power factor of this thing, because if everything is all right, in and out, between neutral and in and out, there is a big inductor. Then your autotransformer basically becomes a really big inductor, and this would fuck up your, yeah, your power factor would be far from 1, where it should be ideal. Yeah. Yeah, the rest of the high voltage side, yeah, this metal oxide, varistor, morph, these capacitor, common mode choke, 2 more morphs, another capacitor, another inductor, and another capacitor. That's all mains input filtering. And yeah, it basically looks like that. Neutral, live, or how they call it, neutral and hot, comes in. There's one big morph, then comes big 1 microfarad capacitor, the common mode choke, 2 more morphs between live and neutral and ground, another 1 microfarad capacitor, the inductor, and then another 1 microfarad capacitor, and that all jogs down to the another sheet, yeah, to that input relay, which can, yeah, that's the filter basically here, which can switch on and off all the stuff, both live and neutral. Yeah, there is, you know, I mentioned that this is basically if the thing is doing nothing, the transformer is a big inductivity between live and neutral, and yeah, it would totally distort the power factor, and that's what this capacitor is for, 2 microfarad between parallel to the windings of the transformer. That should correct the power factor somehow. Cheap way to do it, the easiest way. We have a little current measuring transformer. It's really only half a winding, yeah, the wire going through the core. So this is the input which we want to measure, and the windings around it give you a signal. That is placed, interestingly, here on the neutral out. And there was a second current measuring transformer, and I could not exactly work out how that was placed. It was initially here, but it seemed to be placed on the hot side out. So yeah, I'm not quite sure why they do that. They have their reasons. Otherwise, on the hot side, there's not much more. Here, that's possibly for the input side. This is optocoupler, so they're measuring the input voltage. And here on the output side, yeah, near the transformer is another optocoupler, and yeah, this will be probably measuring the output voltage. Yeah, and that's all for the high side. And the low voltage side, I mean, we had here the battery in, and this goes to the low voltage side of the transformer. And now we come to the part when our mains voltage is yeah, gone, failed completely, or our brownout or our peak voltage gets too high to just clicking some relays and going through different windings through the autotransformer to neutralize that. Then we switch over to battery power, and the battery power basically comes in here. There's a little a big capacitor. It's 40 volts, 1500 microfarads, and then we have a big H bridge driving the transformer coil. And yeah, each part of the bridge is a double MOSFET. Yeah, I jotted down quickly so I can show you. So that's basically the topology they use. Yeah, as I said, the H bridge, plus from the battery, minus from the battery, and the current flows either this path or the current flows this path. And so they can induce an AC, a very high current AC into the, yeah, can we call it the secondary winding of the transformer? So up to now we just looked at this side, at the autotransformer side, but basically it's a combined transformer and autotransformer. And as I said, if the mains voltage fails completely in some way, I mean, it's a UPS, they take the battery power and they induce some AC through that secondary winding, which is in that case that becomes a primary winding. Yeah. And yeah, I guess they also use that winding to charge the batteries. And yeah, but yeah, I forgot something. They have this big capacitor, electrolytic capacitor on that side. Yeah, 1500 microfarad. Yeah, but this is all the high voltage side, everything. And yeah, now we should have a closer look at the digital stuff. Oh, there's a piezo buzzer, or at least a buzzer. Another transformer. Oh. And, oh yeah, I looked that up. Can you read that? Oh, probably. Yeah. LM317T. So, linear voltage regulator. Probably for all that stuff. And yeah, we have a closer look at that too. So, we're just going over the board. Yeah, the MOSFETs are HRF 3205. Then we have a SCUDI. That one. Yeah, let's continue on that row. The 317. And yeah, I removed the sticker from the big one, but yeah, unfortunately the markings are no longer readable. I guess it will be exactly the same here, so I don't go through the trouble. Oh yeah, I go through the trouble, obviously. That's one sticky sticker. Oh yeah, maybe, just maybe. Yeah, the ST part. Okay. Going on. Yeah, as I said, I will read that from the video and then put it into the description. Okay. More ST parts. This looks like Texas Instruments or something. More Texas Instruments. It's a small one. I can't really read it. More Texas Instruments. More ST. What's that little thing here? Texas Instruments. Can't hardly read it. Okay, maybe I'll find that too on the internet. Yeah, it's sorry, battery cable. It's really surprising. Okay, I can't make that out. That's easier. Big diode. And some more ST jobbies. They're all the same. Yeah, they're all the same. And that's it for the digital side of the board. I won't even try to trace that out. Nice shot of the front. Yeah, we looked at an APC Smart-UPS 750. Okay, bye.